So we're switching gears, and it's important switching gears. And we're kind of building up to, this unit talks about chemical equilibrium, and the next unit we're going to talk about pHs. It's funny because from my perspective, I get people who in grade school talk about pHs, hydrogen ion concentration. And it's not until actually this late in Chem 2 can we actually describe hydrogen ion concentration in terms of chemical equilibrium. So anyway, we're going to talk about equilibrium first. So we've talked about equilibriums already, and something might ring a bell when we get to that part. But in general, an equilibrium is something kind of going back and forth. We're going to talk about our generic chemical equilibria first, momentarily, where we have two reactants, A and reactant B, and they actually have stoichiometric coefficients we're going to use in this topic. And they are proceeding from left to right to form two products, C and D, and the stoichiometric coefficients of C is this, little c, stoichiometric coefficient of D is that, a little d. But it's going from left to right, and it's also going from right back to left again. Thus the two-way arrow, chemical equilibrium. We call it dynamic because it's kind of, well, it's not steady state, it's changing. Instead of doing this sort of thing, we usually just go an arrow like that, an arrow like that. So chemical equilibrium going back and forth. Okay. So we're assuming if it's at equilibrium, the rate at which it goes forward is equal to the rate at which it goes back. And if it's at equilibrium, that means actually these molar concentrations are constant. And these molar concentrations are constant. That's by definition equilibrium. Okay, and to kind of show you how that works, we have this still image of these jugglers. And you can kind of see it's captured, and it's really kind of nice because it's got, we can kind of have that archway kind of separating the two fields. We have this guy has two, and a third one in the air, and a white one there, white one up in the air, and two right there. So it's actually, this actually is good but not good, because when something's in chemical equilibrium, it doesn't mean that you have equal on the same side. It just means that you have it's fixed. Okay, so in that sense, it's not a very good thing. But it's dynamic. If I were to animate this, you'd see them moving, okay? This guy throws one over here, and another one, and this guy throws one back over there. So that's why it's dynamic. So here's a chemical equilibria. We have the reactant going to form product, and we have the product going back to form a reactant. This is we're going to see a lot of these, or these are quite helpful, where we have time along the x-axis and we have concentration along the y-axis. Mm-hmm. So in this particular situation, looks like we started out with zero product, we started out with this much reactant, and can you see where the dotted line is? If you give it enough time, it's going to reach these equilibrium concentrations. Okay? Here it's not an equilibrium, here it's not an equilibrium, but here it finally is. We have a steady concentration of both the product and the reactant. Notice also that our reactant didn't go all the way to zero. We still got some reactant left. Makes sense, because we form product and product goes back to form reactant. Okay? And it's that equilibrium that we're going to kind of talk about, those equilibrium concentrations. Okay? Here's another example. Again, the same chemical equilibria, but notice that we have different concentrations. So looks like, wait a minute. Oh, this is rate, sorry. This is looking at reaction rate. The rate in the forward direction starts out hot and heavy because there's no product. Once we start to get product, the product starts to come over. So we have a rate increase over here. At equilibrium, the rate in the forward direction is equal to the rate in the reverse direction. Okay. This is a chemical equilibrium, sorry. This is an equilibrium. It's like a physical phase equilibrium. Bromine is one of the two elements that is a liquid at normal pressures and temperatures of Earth. The other one's, of course, mercury. So here we have liquid bromine, okay? But actually, it's induced dipole. Induced dipole can break, and it goes from a liquid into a gas. So that kind of hazy brown fume there is bromine gas. We have basically the space in the region above the liquid bromine is saturated with bromine vapor or bromine gas. And I think we probably looked at this when we talked about phases, that actually some of that is going to condense back down from a gas back to a liquid. So it's in what we say equilibrium. All right. This is where I say don't blame me, because we've got another K coming up. Oh, gosh. The equilibrium constant. It's part of the equilibrium constant expression. I think you're going to like these. Let's see what you think. So we have this chemical equilibria. Okay, so up there actually is what I've drawn here, where we have two reactants going to form two products. It wouldn't have to be 2 and 2. It could be anything. But the equilibrium constant expression takes on this form, where that big C is the equilibrium constant. And then we have is equal to, in the numerator, we put our products, in our numerator we put our products raised to their stoichiometric coefficients. It's not the same thing as reaction order, because here we're talking about chemical equilibrium, not reaction rates. So sorry about that. You have to chew a piece of gum to get that taste out of your mouth. This is an equilibrium constant expression. And then in the denominator, we put the molar concentrations of the reactants raised to their stoichiometric coefficients. That's it. That's your first look at the equilibrium constant expression. And so equilibrium constant. This is going to be a number. Well, obviously going to be a number. And it simply says at equilibrium, we have a mathematical relationship between our products and the reactants at equilibrium. And this is what it is. That's pretty cool, I think. For now, these little superscripts, these powers we've raised our molar concentrations to, they are the stoichiometric coefficients of the reactants and the products. But it's always, and I'll emphasize it here, I have 2 colors. It's always products over reactants. You're like, who figured that out? I don't know, that's pretty cool. Okay, so your equilibrium constant. Equilibrium constant is another K, but it's a big K. My husband, Dr. Snipes, he thinks he's funny. Well, he is kind of funny. So he said, when will chemists ever learn that constant is spelled with a C, not a K? I think it might be spelled with a K in German. I don't know. Anyway. All right. So this value is something you can hang your hat on, but it's specific for temperature. And but it's independent of the initial concentration of the reactants and the products you start with. Okay? So we have all sorts of options with regard to what you start with, and actually what you start with has got to be calculated in what you're going to end up with, but mathematically what you end up with at equilibrium, this mathematical relationship has to be equal to Kc. Okay, so it's just kind of cool. So here is equilibrium, where we have 2 reactants going to form one product. Remember, it's going to go back and forth. In this particular scenario, looks like we're starting, I think I have 3 scenarios to show you. In this case, we're starting out with 1 molar of each of the 2 reactants, no product. At equilibrium, you can kind of see where we kind of deadpan the molar concentrations of the 2 reactants and the product. Here's another scenario. If we look at this scenario, it looks like we started out with 0 reactants. You're like, how did you do that? 0 reactants, we started out with all product. So the product is actually, it's going to have to go this way to establish an equilibrium. The product molar concentration decreases, the molar concentration of the reactants have to go up to establish equilibrium. If I were to have real numbers there, by the way, I guess just for the record, what this looks like is we can write the equilibrium constant expression, and it would look like this. I think they're fun to write. They're funner to write than the rate law expressions. Kc is equal to, we always put the products first, the molar concentration of the CH3OH in the numerator raised to the first power divided by the molar concentration of the CO raised to the first power times the molar concentration of H2 raised to the second power. That's it. And I mention that because if we were to take these molar concentrations in the gray, plug them in to get a Kc value, that would be the same Kc value we would get by taking these molar concentrations in the gray and plugging them in. It's like magic. It's not neat, but I think it's neat. In this situation, we have a little bit of everything. We have 1 molar concentration of the two reactants, 1 molar concentration of the product. You let it kind of duke it out, and you end up with equilibrium concentrations of each of them. All right. So like I said, this was the equilibrium that was represented in those 3 scenarios, that your Kc will be the same, as long as it's the same temperature for each of them. So OpenStax has a kind of a fun way to look at it. They give you this chemical equilibria, CO and H2O reacts to form CO2 and H2. We could write the equilibrium constant expression for that. And it looks like this. CO2, H2, both raised to the first power. CO, H2O. That's assuming that they've balanced that for me. But this actually says before the reaction. So this is before equilibrium has been established. So this is to say, we'll be doing a little bit of this after break. Well, you know, like this one has only this color, these are the two reactants. This only has the reactants. So you know it's not an equilibrium because there's no product. Okay, this one has all the products, this has a little each of them. But in any scenario, if that's what we start with, we turn it loose and it's gonna reach, you know, equilibrium concentrations according to this equilibrium constant expression. Okay. I'm going to show you these two side by side, but this is the same scenario where the first one was all reactants, the second one all products, and we'll finish here. And we could prove it to ourselves, and I think I've done it before, where I could take these molar concentrations, plug it in that equilibrium constant expression, and get the Kc in all cases. And here they are side by side. This is before the reaction, this is not at equilibrium, and this is like it says at equilibrium. I don't know what else to say about it. Equilibrium constant expression down here. I guess one thing I could add, notice that this particular K, equilibrium constant, doesn't have the C, okay? That will become more, how do I say this? Sometimes we don't put the C, and if the C is not there, our concentrations are in moles per liter. So don't let that throw you off. I'm going to show you a proof of why this is. I hope I convince you, but maybe not. But I'm a stickler for units. I am. As I think people who teach physical science should be a stickler for units. But I'm going to tell you that all equilibrium constants are unitless. Unitless. You might be like, now how could it be unitless? Because these are molar concentrations, so it should be some sort of moles per liter. And I'll kind of show you why that is. So if we pick on this equilibrium, we can kind of come up with a correction factor, okay, where our these C naughts are actually 1 mole, 1 molar, okay. So I'm going to insert these. I can go ahead, this is my equilibrium constant expression, and if I go ahead and introduce C naught for each of the species involved, that it just has a numeric value of 1, but has units value equal to molar constant moles per liter, that actually then won't change the number, but it will make the units cancel. The best way I've explained this one ever so far. So here we introduce moles per liter squared, but the C naught is actually moles per liter raised to second power squared, and then those units cancel, but the number is the same. So your case in C is the equilibrium constant has no units of nothing. All right, so this is a general trend that's going to be helpful for you to kind of find your way around equilibria. So since the equilibrium constants have the products in the numerator and the reactants in the denominator, I hope you buy into this. If you have, we're going to kind of show you very large KCs and very small KCs. But like this says, if you have a very large KC, and we're going to show very large by two greater than signs. If it's very large, approximately, what's it say, up to 1,000, then actually that means at equilibrium, you're going to have a lot of product and not much reactant. It, what we say, favors the products. Now, if you have a very small KC, so what does that mean? If it's small, that means you have a lot in the denominator, that's why it's so small, at equilibrium, and you don't have much in the numerator. And what's in the denominator? Your reactants. So when the dust finally settles, you're going to have a lot of this and not much of this, just based upon your equilibrium constant, regardless of what you start with. And in general, you're talking about 0.001 or smaller. If it's in between 0.001 or 1,000, that means when the dust settles, you kind of have a little bit of product and a little bit of reactant in moderate amounts. These are just general statements based upon the value or magnitude of your equilibrium constant. All right, so what do I mean by big and what do I mean by small? So here are some chemical equilibria. These are all at, let's see, looks like it's, it tells you what temperature that constant is valid at, equilibrium constant. So this is the 298K, which is about 25 degrees Celsius. You're looking at, for this equilibria, 1.4 times 10 to the 83rd Avogadro. That's bigger than Avogadro's number. Yeah, bigger than Avogadro's number. So anyway, so at equilibrium, it basically, you're going to have very small amounts of this. It's what we call product favored. Okay, in fact, it's almost, I would say, to completion with that high of one. Here's one for you. And let's look at what this one. Well, I guess this is one. I thought this was only. So calcium carbonate decomposes to form calcium oxide and carbon dioxide. At 298, 25 degrees Celsius, it's very small. Again, a very small Kc means that you have a lot in the denominator and not much in the numerator. Well, what's in the denominator? Your reactants. It means it just barely budges off of going from reactants to form products at equilibrium. These are equilibrium concentrations. Notice if you jack up the temperature, then you're about, your equilibrium constant is about 1, which, if you jack up the temperature, you can go ahead and force it in the forward direction. Here's one for you. Again, a moderate equilibrium constant. At equilibrium, you're going to have moderate amounts of reactants and products, but it's dynamic. Remember, it's going back and forth. The last one is another small one. It means it does not proceed from left to right. Okay, very much. It's at room temperature. It is definitely reactant favored. But we go ahead and jack up the temperature and we get a moderate one. So then it does proceed from left to right and give you moderate amounts of product. All right. So you need to be able to write your equilibrium constant expressions. So this one would be, remember it's always products over reactants, raise their stoichiometric coefficients. So Kc here would be the molar concentration of O3 squared divided by the molar concentration of O2 raised to the third power. You guys have all this written down, don't you? And this one, the equilibrium constant expression looks like this, where we have the molar concentrations of the products raised to their stoichiometric coefficients divided by the molar concentration of the reactants raised to their stoichiometric coefficients. Okay. It doesn't seem too difficult so far. There are a few catches I'm going to kind of show you to watch out for. Here's one of the two catches I'll talk about. If your equilibria is occurring in water, water should not appear in your equilibrium constant expression. How do you know it's appearing in water? Well, you just you look for your AQs. If something's AQ, it means it's occurring in water. And the reason you wouldn't want to put water in your equilibrium constant expression is water's everywhere because it's a medium, and so it's relatively constant. So this would be an example. You see the AQ, the kind of tell sign that this equilibrium is occurring in water medium. So it might look like I should put the molar concentration of H2O raised to the first power in the denominator, but I'm not gonna. Okay, so this looks like this. Again, just keep in mind for writing equilibrium constant expressions, it's the molar concentrations of the products raised to their stoichiometric coefficients divided by the molar concentration of the reactant or reactants raised to their stoichiometric coefficients. But water does not appear here. Okay. By the way, this seems like a relatively small equilibrium constant. So if it's small, it's going to favor the reactants. And by favor, I mean at equilibrium, there's going to be more reactants than there is product. Sometimes I get these mixed up. The second little tip is if you look at your chemical equilibria and if you have a little S or a little L, S meaning solid or L meaning liquid, next to any of your species reactant or products, they don't appear either. And here's an example of that, where we have a solid next to the ACl, or AgCl, excuse me, silver chloride. It's occurring in water, but I don't have H2O to worry about, but this won't appear in my equilibrium constant expression. So it feels kind of weird, but your equilibrium constant expression, it's products over reactants, so it simply looks like this. By the way, the equilibrium constant expression for this is relatively small. And if you look at what this is describing, we'll be talking more about this specific type of little chemical equilibria, but this is a dissolving process. We're just simply trying to take solid AgCl, silver chloride, we're trying to dissolve it into its ions, silver chloride, silver ion, and the chloride ion. Well, the fact that it's relatively small means that it favors the reactants. So at equilibrium, that means we have a lot of reactants and not much product. What does that mean? It means it's stuck. All right. Here's another one for you. And I mentioned Kc, and we actually have a Kp and a Ka and a Kb. Oh my gosh. But if we mix it up a little bit, and instead of molar concentrations, if we go with partial pressures, we can do that. But we have to I'll show you the link. If instead of molar concentrations, we're talking about partial pressures of gases, of the products and the reactants at equilibria, that actually then is going to create something we call a Kp. Okay? But it still exists. In order for this to work, for gas phase reactions, everything needs to be in their gaseous state, all reactants and all products. But it happens. Okay. So again, don't blame me, but this is where then I introduce another equilibrium constant instead of Kc, and I kind of mumbled a little bit ago. If you say a C there, think in terms, although this kind of says it could be partial pressure, but I think of it in terms of molar concentrations of the products and the reactants. KP means we're talking about partial pressures. So I'm going to talk you through a proof as to how we link KCs and KPs for gas phase reactions. So if we start with the KC, this is what we're going to end up with. And I'm going to show you proof how we ended up with that. Well, I guess I'm not going to show you proof. I'm going to link KP to KC. So let's just say your two reactants, A and B, and your two products, C and D, are all gases. Then we can talk about their relative concentrations in terms of their partial pressures. So P sub C would be the partial pressure of the product C raised to its stoichiometric coefficient. P sub D is the partial pressure of the product D raised to its stoichiometric coefficient. You get the idea. P sub A is the partial pressure of the reactant raised to its stoichiometric coefficient. P sub B, partial pressure of D raised to its stoichiometric coefficient, is equal to a different equilibrium constant, Kp. Okay? So just like Kc is unitless, also Kp is also unitless. All pressure is supposed to be unitless, but I didn't know that. But your Kp is unitless. Okay. So let's say we have this equilibria, and let's say we know molar concentrations and partial pressures. Well, how would the Kc from molar concentrations be related to the Kp from partial pressures? Well, if we look at the ideal gas law equation, PV equals nRT, and we're trying to come up with, well, how would we talk about molarity in terms of that gas? We can rearrange PV equals nRT to get molarity. And what is molarity? Molarity is moles per liter. So if we rearrange PV equals nRT to solve for N over V, that's moles per liter. And I think when we talked about gases at the end of Chem 1, we called this the molar volume, I want to say, or molar density, no, molar density maybe. But anyway, for any given gas, that's equal to the pressure of the gas divided by RT. All right. Well, we need to consider each of our four species, change these molarities based upon this, and it looks like this. Well, I'm going to use this pattern, I should say. If we focus on just the reactant A, the molar concentration of A would be equal to the partial pressure of A divided by RT. Okay, so I go ahead and take that through for my two reactants, my two products, and I get something that looks like this. Now, equilibrium constant Kc, in terms of basically now using partial pressures instead of molarities, looks like this. Where, again, it's the products divided by the reactants raised to their stoichiometric coefficients. But instead of moles per liter, I have the partial pressure of each over RT, partial pressure over RT. Okay? Well, we're going to want to cancel out those R's and T's and kind of bring those exponents together, but you have to be careful. If we take those exponents into the quantities, so the next slide, basically, if I take this exponent into this quantity, what does that look like? And here's what it looks like. So I'm going to take my exponent into my partial pressure, so it's the partial pressure of C raised to its stoichiometric coefficient, and then I have 1 over RT also raised to C. I do the same thing with D, partial pressure of D raised to D, 1 over RT raised to D. And I do that for the reactants in the denominator.
And you use this like when you have partial pressure and you're trying to find molarity?
I am showing you a proof, kind of behind the scenes. I'm going to show you one more relationship between Kc and what I'm going to call Kp. So I'm just kind of showing you the logic. I'm showing you the logic. So there is going to be a blue box here in a minute that's going to be like, oh, well, that's something I would use on a test. This is probably what you wouldn't use on a test yet. but it's kind of what's going on behind the scenes. It's to try to make sense of why we get the blue box equation. So if I'm going to kind of pull my terms together, it's kind of messy if you ask me. I have 1 over RT terms. I have 2 in the numerator, 2 in the denominator. Actually, if I pull the 2 in the numerator together, I'm going to get 1 over RT raised to the C plus D. If I pull the 2 in the denominator together, I'm going to get 1 over RT raised to the A plus B. But since it's in the denominator, I actually have to end up subtracting that. So it's all legit. Whoosh! So that leaves behind my partial pressures. So we have the part, now this is looking like something a little tameable. Actually, doesn't this look like what I said KP was going to be? But it's still KC. So anyway, what do we do now? All right. So this right here, this power of 1 over RT, if I look at it, actually it's what we can call the change in moles. Because these are stoichiometric coefficients, the C and the D and the A and the B. Okay? So if I define change in moles, that's just, it's always final minus initial. So it's like whatever these end up, from that subtract whatever these end up, the sum of these. That's what the power of 1 over RT is. So, one of the things we know about anything raised to the 0th power, it's 1. So if I go back here, sorry, it's 1. Yeah. If this actually is a wash, if this is 0, that term becomes 1. If that term becomes 1, then your KC is equal to your KP. Okay. So, I don't know if this might be this might be something you asked, how will I use that? Well, this might be something that you would use. I have a blue box coming up too. So in other words, the way you would use this, if I know KP and I want to find KC mathematically, what I would do is take 1 over RT, you need to add the temperature of the equilibria, R you look up, and I would raise it to a power, whatever the difference in the moles were. So for instance, that all that means is, I'll just throw in a number, like if I have, 3 and 1 and 2 and 1, okay, the difference would be, I have delta N, this isn't working very good, but it's equal to 4, because it's the sum of those, minus 3. That's your delta N. And I would plug it in there, and I would come up with my KC, give my KP. Another form of that looks like this, a little more flattened out version. If in this case I was given my KC and wanted to find my KP, here's what that would look like. I would take my KC and multiply it by RT raised to whatever the difference in the moles is. Again, it's the sum of the product moles minus the sum of the reactant moles. Okay, and then for the, we're back to using what I think of more as a gas law, a value of the ideal gas law constant. That's at 0.082058 liters atmospheres per mole Kelvin. This is probably where a minute ago I was like, oh, I don't remember reading that on a slide, but it said that the partial pressures of your gases need to be in units of atmospheres, and that's probably where this is coming from. If you're using a different value for R, where units of pressure are in milliliters mercury, like the way I learned it years ago, then your partial pressures need to be in milliliters of mercury.
So in that flattened out equation, the temperature is in units of Kelvin?
Yes,
okay.
Definitely. Okay. This is all gas pressures on the atmosphere, but like I said, if you use a different R, then you can use different pressure pressures. All right, so let's look at an example. So this will only work if all reactants and products are in their gas phase. This meets that criteria. So we have a KP value, and we're supposed to knock out KC. So let's do it. The delta N to me looks like 2 minus 1. So the delta N is going to be what, 1? Okay. And we're going to bring back up that formula. I can't remember if, I'll ask Carl if you get an equation sheet for this unit. And like you said, Daniel, we need to make sure that our temperature needs to be units of Kelvin. So if we take 45 plus 273, you're looking at 318 Kelvin. All right. So again, your delta N is 1, temperature's 318. So we can actually need to do a little bit of rearranging for this one. Divide both sides by divide both sides by RT delta N. And it looks like this. Our KC is equal to KP over RT delta N. I'm ready to plug and chug. So again, KP and KC values are unitless. And actually, since I know KC is going to be unitless, notice I kind of wimped out. I'm putting my units here for my R and my T. So it'd be 0.62 divided by, in the denominator we have 0.082058. And then also in the denominator we have the temperature, 318. 2 sig figs, then the corresponding KC will be 0.024. Which is a moderate sort of magnitude. So you expect there to be at equilibrium, I'll say similar amounts or a sufficient quantity of both reactants and products.
So KC is unitless too?
KC is unitless. KP is unitless, yep.
And KP too?
Yeah, KP is unitless, yep. All of our equilibrium constants. And so yeah, there's a KC, a KP, there'll be a KSP and a KA and a KB. They're all deal with the equilibria. You're like, really? They just switched the little subscript. Oh yeah, but they're all equilibria. So, but still, we're like, what? Okay, very good. That puts us where I want to be. And then no class next week. And spring's coming.
Can I check my lab things in this?
Yeah, you should be able to. Yep. I'll open it up for you.
I was looking for the paper, but it wasn't there.